It's Mike. Great. Great to see so many of you here today. uh, Good afternoon. I'm very pleased to introduce to you Martin Vallières, if you don't already know him. Martin is coming to us from just across the railway track there, from the Glen site, where he's based at the Cedar Cancer Center. He's a medical physicist, a rare breed of people, and very glad that I was just remarking to him that after having studied medical physics, he actually, in McGill, he took a detour and became an assistant professor of computer science at Sherbrooke University, but thankfully has returned to medical physics and is involved with the very active unit over here at the Cedars Cancer Center. He's also an associate member of MILA, the Quebec AI Institute, and happens to hold a Canada CFAR AI chair. All right. Well, congratulations. Not a simple accomplishment. His research activities are focused on development of predictive models for personalized medicine along three main axes: medical image analysis, heterogeneous data modeling, and federated learning. Yeah, I hope to be educated about that last one, especially. I'm always like, sounds like a very important topic. And all right, all right. And currently, Martin is an associate professor at the Department of Oncology at McGill University. And he's also one of the 5 co-directors of the Réseau Santé Numérique of the FQRS Santé. Thank you.
Thank you very much for the introduction. It's a pleasure to be here, to be at the core. I don't think I'm on the mailing list, but I think I'm part of 4. I'm still located at the Glen. So I don't have an office here, but we're not so far away. So it's a pleasure to meet you all. Please drop by at the Glen to see us at the medical physics unit whenever you want. And today I'm going to talk to you, about integrative modeling of heterogeneous data in medicine. A bit of a concept that I hold dear in my research, integrative modeling. I'll try to explain that to you as best as possible. For explaining to you basically where I come from, you've done a great job of explaining basically the basics of where I come from. In terms of research, I wanted to show you this concept, and here there's a bit of a glitch between what I wanted to show and the slide here. So trying to, it's over there. Okay, good. This is supposed to be a theta, okay, for those who are online. Theta, yeah, a theta, like this here. So it's just to say it's an interesting point of view from that person in 2022 already, but that says 2 types of academic researchers: those that dives and those that surf. Diving research would mean a spot in the ocean, a research subject where you dive deep in it, so deep and narrow research, whereas there are also surfing researchers, or more surfing researchers, where you cover a broader spot in the ocean, a broader area of the ocean, but you cannot go as deep, obviously. But there's obviously things in between, I think. And in my case, I think throughout my career with this theta, so the greater the theta, okay, the greater you dive. I think I've been a diver in my life. I've been also a surfer, but now I want to be an interdisciplinary researcher. So right in between, theta 45 degrees. That's my goal. Let's call it like this. So just to summarize quickly my academic journey. So I was in the medical physics unit of McGill University for my master's and PhD in the years 2010, where I did. This is the theta here that's supposed to be there too, where I did got expertise in radiomics, quantitative image analysis, medical image analysis, and machine learning in the domain of oncology. For example, that's an example study where from pre-treatment MRI and PET images, we extract quantitative imaging features, do machine learning with those features to predict different types of outcomes of patients affected by cancers. For example, if patients are more likely to develop lung metastases in sarcomas, for example. That's the type of predictive modeling that I used to do back then, that I still do. Then afterwards, got a bit more of a surfing type of research during my postdocs, with trying to integrate into the modeling different types of data, including text notes and the EHR types of data. And that's one article that resulted from this postdoc work with my good colleagues in San Francisco. Then, as mentioned, with this background, I got hired in Université de Sherbrooke, affiliated also with the Centre de Recherche du CHU, where I try to develop a program in heterogeneous data modeling for better precision medicine. And that's where I started really to surf, in contrast of having dived in the ocean of research for all those years. And when I say heterogeneous data modeling, I mean trying to take into account the whole realm of data types that are available when treatment decisions need to be made. Basically, not being an expert in all of these types of data, but rather trying to provide the means of combining those data sources together into useful predictive models. That's about it. So from 2010 to 2024 or now, I went from medical physics to AI for health in general. So from diving to surfing. And now came back at McGill, trying to build a roadmap to precision oncology or precision medicine in general. More about it with in terms of generalist, specialist, and precision AI. Let's go right through it. The overarching goal of my research, in the sense that that's what I want to do in life, is contribute to better precision medicine. Okay, I like to put back this quote of President Obama in 2015. That's basically the definition of it: delivering the right treatments at the right time, every time to the right person. Try to do this. Fundamental purposes of my research that I think about every day: transparent co-creation of AI. I think with diverse stakeholders can help. Okay, democratic AI can help in our research. Interdisciplinarity is key if we want to progress. And I'll show you software at the end of this presentation that I think enables better accessibility to AI. So that's, I think, my contribution to having interdisciplinary work easier interdisciplinary work among us. And generalist medical AI is not sufficient, in my opinion. What is generalist medical AI? And what I mean by that is that specialist and precision medical AI is also needed. What do I mean by this? Try to explain it quickly, but when I refer to generalist AI, I'm thinking about those foundation models, those beautiful foundation models that are being developed in the very last few years. For example, this one in 2023 already by Google Research, MedPalm that basically is able to integrate all sorts of different types of data together, and in single big foundation models is also able to do all sorts of multiple tasks. That's basically general way of seeing generalist AI. But I'll talk about today something that is a bit more precise, or let's say specialist, that could complement generalist AI. And when I talk about precision AI, I think it's the very last step that we have to always try to get to. Here is the basic of life in cancer, for example, or in medicine, in health. State of a patient, X, we extract features from it that will influence the treatment that we're going to give to that patient. The treatment obviously will influence the outcome of the patient, and features also obviously influence the outcome of the patient. So the basics relationship of diseases, and all those relations here needs to be taken into account as a function of time. Precision medicine is thus adaptive to changing patient conditions. Actually, I didn't put the function of time here, but this evolves all the time. That's what precision AI would all be about. But today I'll focus more on spatialist AI. Okay, I think this all needs to be integrated together, and sometimes there's depends on the task that you're doing, but there's more room for generalist AI or precision AI sometimes. But in between, there could be, I believe, specialist models that complement full generalist AI, and we could think of specialist models here, or in specialized medical domains, as small models that can be part of some agentic system, for example, with the development of agentic AI nowadays. So that's basically the overview of the program, let's say, making those links between those different types of AIs. But today I'm going to talk more about this. Okay? Integrative models, specialized medical domains, predictive modeling. Sorry. Okay. And that's going to be divided into 3 parts: prediction, validation, optimization. Prediction. So here's, again, the beautiful graph, causal graph of life and health. In predictive modeling, basically, we don't take into account this part, the arrows that are between X and T and Y. Basically, in predictive modeling, we only take this into account, okay? Trying to predict outcome Y given the state of a patient X, with the huge and reasonable assumption that all patients receive the best treatment possible. So we don't take into account basically the different types of treatments that we just assume that they receive the best possible treatment possible. The best possible treatment, sorry. So in the end, the game is, we call it simple in the sense that we're trying to simply model the probability of observing some outcome Y given the state of a patient X. So trying to find a function that maps X and Y. That's an example of predictive modeling. Try to find a function f that maps X and Y, the one that I presented earlier, early prediction of lung metastases in 2015 for soft tissue sarcomas. When patients arrive at the hospital, you're in a certain state. We try to capture that state, for example, with medical imaging. We extract features from that, and we try to predict if basically the sarcoma, the tumor of the patient, is more aggressive than they're more likely to develop lung metastases. So X, as I said, can be, here in that study, it was radiology or MRI imaging. But there are also the types of data that are available, like text reports, multi-omics profile, if it's available, and all sorts of demographics information. So that's basically an overview or a summary of kind of the realm of information that you can have given time for a patient, for example, that presents at the hospital with sarcomas. This is what we call multimodal data. Well, I'd like to make the point, or call this today heterogeneous data. And I'll explain that a little bit later. Heterogeneous data. So the question is how to model X, how to integrate all this into a predictive model that makes sense given the very different types of data that we have. The core algorithm that we use to do this is called the graph neural network. And just quickly, it's a neural network with graph relation. Here, this is a schematic view of a neural network that I'm sure you have seen many, many times, but that with all the functions that allows you to develop a function f that is nonlinear, a function f that maps the input x as a function of y. Sorry, y as a function of x, with all those relations and connections that creates a nonlinear function. Good for a graph neural network. You basically have graph relations integrated at hidden layers, but also at the very beginning of the network with the different inputs here. That's basically the essence of it. It's combining the relational inference of graph models with the power of neural networks. to exploit those maybe useful relations between the variables for a given disease, to predict a given disease, and the relations between patients also for predictions. What I mean by that is you can, for example, exploit the relations between the variables to enrich actually the representation of the variables to do better prediction. But you can also exploit the relation of your neighboring patients that may have similar trajectories as you, from which you can base yourself to do better predictions for yourself, for example, in a graph neural network. So that's here already. It's a two-level graph, one that connects variables and one that connects patients. That's can build a graph neural networks with two levels here. So, and here is an example of a type of graph neural network that has, and it's beautiful, that has maximum relations embedded in it. Relations between patients, relations between variables, relations between different types of modalities, all sorts of connections are there, and it's actually a beautiful concept. It's just not really scalable actually because there's so many connections. So we're trying to find a way to reduce the number of connections only to find those that are relevant for a given prediction. So that's beautiful. It's beautiful model-driven fusion of multimodal data, but not necessarily a fusion that takes into account the data in itself for the fusion. It just does everything at the same time. It's not considering also data as heterogeneous. So what do I mean by heterogeneous data? Quite simple, actually. In my view, medical data is this type of data here is heterogeneous in the sense that it's multimodal. It consists of different data types. Good. Demographics, imaging, text. Good. But it's also hierarchical. And that's a word I have the difficulty to say that I'll say a lot today. I guess I'll take a sip of water just for that. Can someone say it for me? It's acquired at different biological scales. Genomic scale, anatomical scale, where we capture with medical imaging, we capture the information at the anatomical level, and demographic scale, where that represents the whole the state of the whole state of a patient, for example, the age, global variable for the patient. So it's acquired at different biological scale, hierarchical. Hierarchical. So this plus multimodal equals heterogeneous. So integrative modeling takes into account this hierarchy and LT when learning patient representations. So different scales, X, Y, Z, I think you get the point, that have a certain order, a specific hierarchy actually that we need to take into account. Here I just put the arrows here to say that we're also trying to exploit the cross-modality interactions, not just hierarchy, but also the cross-modality, the relevant cross-modality interactions that could help for predictive modeling. And this could be explored, that space or that environment of cross-modality interactions with reinforcement learning. So here's the workflow quickly that we're trying to build and that we're testing against other frameworks like the one you've seen, the Max Core one that had all those possible relations, trying to see if we can come up with something that is flexible, modular, that allows us to define the hierarchy and at the same time that flushes out things that are not relevant, those relations that are not relevant for a given predictive model. Basically, it goes like this. We're not trying to be the best in multi-omics analysis or imaging analyses. There are already expert analyses that exist here, exploit or represent the data at the scale of multi-omic data or at the anatomical scale with medical imaging. There are some expert analyses. That's something kind of old here, DenseNet, but it's still useful to exploit imaging, to extract imaging features basically at this scale. That's just an example. And the old the old transformer, which will always be very useful. Example that it was used to pre-train that clinical bird that already dates from 2019, but that can still be useful to extract features from medical notes. There are obviously other types of LLMs that can be used for this purpose as well. So there exists expert analyses. You can use them in this framework. There's also expert fusions, like I've shown before with the max score paper. That's an example of an expert fusion for the multi-omic scale. So people have done it, and it works quite well to fuse and integrate different types of omics data together. Great. That's something you can use right here at this scale here, expert fusion. That's not the exact picture here, but let's pretend this could be the customics algorithm. Then there's these different types of expert fusion like diffpool that basically has graphs embedded in them that discover the graphs and the clusters to create the graphs for the fusion, which is great. Okay, that's another type of expert fusion that you can use at any given level. The idea here is to go in a cascade of fusion. You get a representation at scale X that is very much available to you at the end, that you can at the end explore and not just throw in the all realm of different types of data that is present. So you get this representation at scale X that you can explore and evaluate later. Then you fuse this representation, only then that you fuse this representation with the next one at the next level. You use this plus scale Y to fuse it again. Then you get a representation at scale Y. Then and only then you take this to fuse it with the top scale, the top biological scale, basically. One last fusion step. This is how the framework would basically go. And at the end, you have what we believe is an enriched patient representation at the level of the patient that you can also connect with other patients to further enrich. Plus those little arrows here that can basically enrich the representation that you get right at the start by taking into account the the relations between the different types of variables at the different scales. That's basically the whole thing. So that's what we're trying to show. Is it going to improve performance? Maybe, but is it going to improve interpretability compared to, let's say, bigger black boxes that do all those correlations together, all those relations? We hope so. So we're going to try to see if it leads to better interpretability of those models. And it's meant to work in hybrid mode. For example, the data hierarchy could be learned, but it could be also user-defined. The definition of those scales here, X, Y, Z, could simply be, okay, all those different types of data, here it makes sense, go at this scale. Imaging plus text notes goes here. You can define it a priori before starting the problem, or you can learn it if you want. And the definition of cross-model interactions as well could be defined by the users, by medical experts, basically. So that was part one. I don't know if you want to stop me here, if you have questions to ask at this point. Yes?
Sorry. Thank you. How do you choose the order of the fusion?
Yeah. How do you choose the order of the fusion here?
Yeah.
So basically, you define the order of you define the hierarchy. Mm-hmm. And then so you choose or you learn what goes at the bottom, what goes in the middle, and what goes at the top. And then you always do the same thing here.
But does it matter which one goes first and then the second?
I think it does. In that way of seeing things, this hierarchy of data, of biological data, basically, it would probably, with that same type of fusion here, it would probably not make sense to switch these types of data here. Mm-hmm. First, you put them here because it's the lowest biological scale, second lowest, and so on.
Thanks.
To do this.
Yeah. Thanks.
Wait.
Can you explain a little about the slide that had the reinforcement learning on it?
Mhm.
To how do you like incorporate that in this pipeline?
Yes.
Thank you.
Sure, it's not so far. Yeah. Oh, actually, it's at the end there. Sorry. Yeah. I think it's a supplementary step that could be done after having this, having learned all of this. Basically, you learn things here, you learn things here. Let's say you have already those vectors here. You learn the fusions in a cascade way, which is not that difficult when you think about it. But you do this with different types of fusions. Then after you have a model at the end that gives you this representation of a patient. So you could use this model with a new patient, and poof, it would output this. So let's say you have this model basically that does this. What you can do, either you could either do it while you learn or after. If you want to keep it simple, you could after you have the model that spits this, then you fine tune. You already have something learned. You fine tune it with different relations here, that basically adapts or updates your vectors here. So by putting those arrows here, you'll get an enriched representation of the variables here right at the start.
Thank you. Sort of aggregating over the possible treatments that people would have received. You're going straight from X to Y, averaging over everything else that happened in the middle.
Well, yeah, we're talking about predictive modeling. Yes. If we were to consider treatment, it would be another ball game, but you could start from these things here and include time, let's say,
Okay.
and treatments also.
And what is the reasoning for that? Why do you leave the treatment information out? You're collecting so much information.
It's not that we want to leave it out. It's like the first thing to do.
Okay.
It's assumed that you have kind of an homogeneous cohort that all patients receive similarly the same type of treatment.
Okay.
And that you can then exploit X and Y together.
Okay. Okay. Thank you.
But then the next step is trying to do treatment recommendations, and then causality comes into play, and that's like another ball game compared to predictive modeling. But predictive modeling can be a start. Okay, part 2, validation. So yes, you have those models, beautiful models, good, maybe even causal models. How do we ensure that they stay performant over time? Actually, we have to make sure that once we put them, for example, we deploy them and make them being used in the clinic, that their performance is actually as we expected, as we planned, and as we expected 2 years ago. Later, it needs to be the same thing as well. Or actually, if it's not, we need to fine tune or readapt our models. But how do we monitor if the predictive performance of models stays the same? We're trying to develop kind of this this framework here to do continuous evaluation of predictive models over time per patient profiles. And I'll explain what I mean by per patient profiles. In the sense that you have an evaluation set. Okay, you develop the models here at the MUHC, and you say, okay, we're going to see if it works well in Sherbrooke. You have Sherbrooke in mind. Let's see if it goes well in Sherbrooke. You take the cohort in Sherbrooke, and then you get global performance for this whole cohort. Basically, you'll get an AUC or perfect accuracy for the whole evaluation set in Sherbrooke. The idea here that we're trying to actually provide a tool that allows you to better display if, yes, you have the global metrics, but your model performed equally well for men and women, or old men, young patients, and so on. You get the point, I think. So we want to first subdivide the predictive performance per patient groups to perhaps better detect performance shift, data outliers, and biases. A profile is something that looks like this. A model exists. You want first question you ask yourself, can I deploy it in Sherbrooke, for example? And then you get on your evaluation set in Sherbrooke, good. An AUC, for example, of 0.9, it's very good, excellent. Perhaps we should deploy it. But then the idea is to further analyze within the evaluation cohort how the model behaves for different types of profiles. And that's just an example here. You could have a profile A, women, for example, for which the model would perform less well, whereas for men, it would perform better. And then you could go down into the branch here, the branches here, and define a profile BC, which is men over the age of 55. Okay, so you have differences basically with the 0.9 here is a summary of all those different sub metrics for different profiles. So we're trying to find a way to provide this information quickly to physicians, for example, clinicians that would use predictive models. And this tool that we're developing for that purpose is called MED3PA for Predictive Performance Precision Analysis, 3PA in medicine. The thing is, the idea is depicted here. You have training data. Okay, you build a model. That's a model here. You have, it's a 2-feature model. So X1, that's a scatter plot of X1, X2, the 2 features, for example. And you're trying to build a model that discriminates between the 2 classes, class 1 and 0, for example, more aggressive tumor or less aggressive tumor, better responder to treatment, less worse response to treatment. That's a model that separates the 2 classes. Good. The thing is, that would be built, for example, here at the MUHC. You arrive in Sherbrooke. Oh, you detect that there's another cloud of points here, for which the model doesn't make sense at all. So what's this cloud here, basically? So for this cloud here, you would not want to use the model. And we want to, I mean, in life, we need to detect when another point cloud like this appears, and for another kind of subgroup of patients for which you don't want to use the model. That's what we're trying to detect. So the basics is to calculate the predictive confidence in a given evaluation set. So here, the darker it is here, the less confident you are in the prediction. No matter what is the prediction, you're less confident in those regions. So you need to basically build another model that gives you the predictive confidence. You need to learn the predictive confidence, learn the model errors, basically, individually per patient or aggregated by profile. So that's a profile here. All those regions basically are profiles. So that would be here a profile, this point cloud, this cloud of points at the right of the figure. It could correspond to one of the red boxes, for example, here. So you're trying to detect those cloud of points that have lower predictive confidence. And basically, I won't get too much into details on this, but let's say you consider 100% of the points here. You're at the right here of the figure. You have the right of the figure. You have the global performance metrics are right here. If you start removing, let's say those profiles or those points by profiles that have the lowest predictive confidence, the idea is that your remaining global performance will increase. Then that would be kind of patient profiles, for example, from which you need to take care of those patients of those profiles in another way, of course. But here it would mean exclude some of the profiles and identify those for which you don't want to use the model, basically. And then you can define basically a threshold to the satisfaction of a physician, a clinician that would say, okay, I want here a declaration rate. That's the y-axis, the x-axis, sorry. The x-axis is declaration rate. You say at I want to be at 95%, for example. That would be a threshold that you would use for deployment. That's an example use. That's an example of intended use, basically. Basically, you have model that you build in institution A, let's say here, super cool enriched representation that I've shown before. All right, you want to deploy it at the UHC as well, but in another place, for example, in Sherbrooke. Okay, what do? Good, you could use it directly, like we've been doing. You just transport it, look at model predictions. The idea first you do internal validation and identify, yes, okay, the within the same institution from which the model was trained, for which patient profiles there's lowest performance. And then you monitor that over time also, because you can have data shifts. So the model may change the way it behaves because of many, many different reasons. You need to monitor that over time to see if it's stable. Then you can start external validation into another institution, analyze those trees basically of predictive performance, those NDR curves, and then you have more information to deploy at the other institution. You have predictive confidence, you have what happens per profile, you have the reference metrics by declaration rate curve that tells you exactly basically how the model behaves, how the performance behaves when you exclude patient profile. That's the intended use, and we've applied this to this concept to in Sherbrooke, in Cius de l'Estrichu. The predictive problem here was to classic problem is to predict the hospital 1-year mortality risk, HOMR. It's to initiate actually early goals of discussions about end of life discussions, basically. That's this type of model here uses admission data, but I mean general admission data. It can be any patient, the general admission data of any patient that arrives at the hospital. So it's a very broad and general model. We've done it on 123,000 patients at in Sherbrooke. We learned the predictive confidence. We got this MDR curve, and what it would tell us is that okay, there seems to be a threshold here, a declaration rate from at 95%. So there's a 5% of patients basically from which it could be warranted to not use the model, basically not use it blindly on the 100%. But when you get a profile that is within the 5%, put them aside and don't use the model and deal with them in another way. It led to this type of graph per patient profiles, which that are basically different types of variables. So it tells basically per patient profile if there's the 3PA recommendation is if the prediction confidence for a new patient is low, you got to be careful, or prediction would be approved. And then you do what you could have already done with the prediction in itself, if you're, for example, in the green profile. So this is this is something we have publicized recently. It's on medRxiv for now. It's under revision in Jamia, and that's the software, open source software MedTree on PyPy, if you want to have a look at it. So I'm almost done, because this is package MedTree is part of something grander that I call Medomics, which is the whole platform in itself. MedTree is a sub package actually of Medomics. And Medomics is used, the platform Medomics is used to do what I call optimization, but not in terms of optimization of the models, but optimization of interdisciplinary work to have a better synergy of medical AI interdisciplinary teams. We're trying to build that software so that clinicians and computer scientists can work under the same platform and be in synergy when developing this type of research. So it's a unified analysis platform for clinical researchers and computer scientists that I hope will allow them to work better together into an integrated environment. To do those types of integrative modeling experiment, part 1, and evaluation of them, part 2, that I've shown today. And I have a video basically that summarizes all of medomics. Sorry, I have a slide before. The idea is really to help medical AI teams to better work together. This is just a view, une vue de l'esprit, as we say in French. It's just a traditional paradigm. Maybe there's not as much involvement into data management, AI hypothesis generation, AI computing. There's not as much involvement as we would like from clinical scientists sometimes. They know the problem, they know the data, they know the clinical scenarios. So of course, the idea is that they should get involved as much as possible into the space of data management, generating the hypotheses, the computing, the visualization, understanding the the problem together with the computer scientists. This would create the kind of a more synergistic process, having a common environment, a unified platform. All right.
Despite their essential role as experts, clinical researchers face challenges in accessing essential tools and collaborative channels to use AI more effectively. Bridging this gap requires empowering researchers with resources to drive AI advancements and fostering more collaboration between medical and computational fields. Medomics is an open-source platform designed to support the research community and help medical AI teams to better work together. It addresses these challenges by, first, providing clinical researchers with easy access to AI tools, enabling them to independently run their own experiments. Second, by facilitating collaboration among interdisciplinary research teams, bridging clinical expertise and computational science. And third, by offering computer scientists an integrated environment with access to multiple state-of-the-art solutions. The Medomics platform combines the power of multimodality medical data and a collaborative research environment to drive innovation in personalized healthcare. It empowers teams to develop predictive models for personalized treatments. The Medomics platform offers versatile usage levels, from user-friendly built-in pipelines to highly customizable Python libraries, making it accessible to both clinicians and computer scientists. Its 3 core layers, design, development, and deployment, enable heterogeneous medical data integration, feature extraction, and model training and evaluation, all while supporting decentralized model validation, crucial for secure, collaborative research. Furthermore, the code generation feature is a highlight of the Medomics platform, allowing users to automatically generate Python code from graphical pipelines, creating a powerful synergy between the medical and computational fields. Accessible on multiple operating systems, with comprehensive documentation and an active community, Medomics is ready to support your journey in medical AI. Visit our website to get started and join a community dedicated to transforming personalized medicine through integrative data modeling.
All right. This was the video. You can start if you're interested. You can start from this website, medomics.app. You'll find links to our GitHub where we have the code, the different releases. We're like at version 1.5 right now. Our project board where we have all our basically board and all the cards of the developers that do stuff. You can see it. You can create issues if you want. Yeah, there's a pretty good, I think, documentation on Gitbook. We use Gitbook for that, where you'll find also tutorials and demos. We have our YouTube channel where we try to do good videos to showcase the tutorials and the demos. It's always a work in progress that we have to update them with as the version of the code augments, but it's not that bad at this time. We have also a Discord server if you want to come to chat with us if you have questions. You'll find all those links here. That's what I talked today. Really, the research laboratory that does this. It's my research laboratory at this time that is split between Sherbrooke and McGill, because I have also students in Sherbrooke. I still have also students in Sherbrooke, so it's a nice lab that we have between two places. It's called Medomics Lab. Medomics Lab, the research laboratory, develops Medomics as you have understood. So Medomics is the platform, Medomics Lab is the research laboratory, and we're trying to do research in those three aspects here. Thank you very much for your attention. I think we have.
Is anybody else? Oh, all right. A few questions. I think.
Thank you for the presentation. It was really nice. And about the training, validation, and testing set. In deep learning models, we train on some data. With validation set, we kind of change the hyperparameters to make it work on the validation data that we have, make the model work. And then we test on the unseen data. Here you said that with the validation, we see the model doesn't work on some data. We try to understand that on which data the model does not work, and we remove those data, then we test the model. So it's not that in, for example, other deep learning models that you force the model to learn all the patterns in the data that we have already, then test it on the new data. You remove some part of the data, so the model just works on the data that is more known or passes through those filters. So if we want to use the platform on test it on different kinds of data, all the time we have to pass the data through those filters and remove some data, then we test our model?
It's not exactly that, but I understand the confusion perhaps, and sorry if it wasn't perfectly clear. We start from a model exists. It was learned the way you described with training, validation, tests. You learn a deep learning model. You have one model. You learn it the way you described. It's when you're about to use it, to deploy it. Then you want to know, do I use it or not? And for who do I not use it actually? And if you describe that tree of patient profiles, you'll have a better understanding as to why the predictive confidence for an example patient profile is low, because maybe it makes sense that for patients that for the 1 year hospitality risk, 1 year mortality hospitality risk, there's some profile here that, for example, cancer patients, yes, they're pretty much different than all the rest, for example, is higher. So it's a totally different profile from the rest, for example. So it's about deployment. Now the next step is to do what I think you were stating is, you know this, why not retrain the model, take into account these differences that, that's what we're aiming at in the future. Yeah. You're welcome.
Hi. Thank you for the presentation. Heterogeneity, I understand the way that you brought this into perspective with a lot of different, completely different types of data that can feed into a model and that can be leveled in different ways depending on knowledge and learning. But heterogeneity often comes with a component of, within a specific subtype of data, you have heterogeneity. And that often comes with rarity when you talk about precision medicine. And I know that maybe wasn't the mandate of the presentation, but how do you do some work around that? And are there what are, I guess, the main strategies that you can use?
So we're not thank you for the excellent question. It was one way of using, I guess, the word heterogeneity. There's heterogeneity, as you say, in different contexts. For example, heterogeneity in images or in the sub data type. So there's different levels of heterogeneity. You're right. I think we're not experts, let's say, in dealing with heterogeneous these types of heterogeneity that you describe, for example, but it's kind of a bit of embedded first in part one, because we try to make the model as simple as possible while taking into account all those data types. So if it's as simple as possible, perhaps it's going to generalize better. And maybe we're going to be able to also take into account those heterogeneous data types or heterogeneity between the data types, the way you describe it, with part two, because we're going to know with MetriPA, like sub-patient profiles that have certain data types have lower performance, and we're going to be able to correct later on for that. Part two also tells you, let's say, you could divide the patient profiles, for example, by institution. So you could say, okay, I have 3 data sets that I use to train a model. Do I really use them in an equal manner? Because there's heterogeneity basically between the scanners of in the different institutions, and that creates different types of images. So do I use them just equally, throw them into the model, or consider them differently? And to know that, part two, MetriPA could actually be helpful to define which institution in the training basically makes your model worse, so that you can take that into account. So it's kind of embedded, but it's not the target directly of our research.
Thank you.
Welcome.
Can I ask a question?
Thank you for your presentation. I'm just wondering, maybe you mentioned it and I just missed it, but in terms of your pipeline for the data processing, so can you just talk a little bit more about like the aspect of how it's processed, where it's stowed, and I'm thinking more the ethics piece, you know, when you're applying, is that part of an agreement or your platform, it's just freely accessible? I just looked at your platform, but I'm just wondering
itself, or
yes, do you have a pipeline, or you're just basically suggesting, because you went through various models, but I'm just wondering on your profile, on your website, is there a specific do you offer the pipeline?
Does that answer kind of your question? The ethics. Okay, no, okay, that's yeah. Okay, and sorry, I have some slides that maybe could have also answered your question, and now it's not here. So the basic use of Medomix is you as a researcher having it on your laptop. So we assume that you have all the ethics required to have the data on your laptop. There's another way that another process that we're developing now is that you, from your laptop, have just a light version of Medomix, and you access a server somewhere else that is protected. For example, in the hospital. Where's the hospital? You said it's there. Okay. So you're on your laptop, and you access Medomix server over there because the data is protected there. But it assumes that you can connect to one computer over there, and that's another way of working. It's what, sorry? For ethics or? Yeah.
So we're overriding potential issues that other pipelines offer. Would you say that?
I think it helps to get to the data from the point of acquisition. So basically, in the hospital, if they can, for example, just create a small, let's say, research database just for you on the side, maybe it's less complicated than bringing it here in this building. So it helps to then we can connect with Medomix. We have different like superset. There's a library called Superset that allows you to connect remotely. So we have all sorts of tools, I think, that helps you get to the data where it is in the more secure fashion. But yeah, you have to convince, I guess, your ethics board that that's the way of doing it.
Dr. Bernatsky, go ahead with your question, please.
Your presentation. So do you agree with my?
Sorry,
Yeah.
We just need to increase the volume a little bit.
Okay. I'm going to try this. So can you hear me now?
Yes.
Yes. Okay. So thank you for that presentation. Would you possibly agree with hypothesis that we never should have started using the term artificial intelligence, and that we will stop using it when people, apply more the strategy that you have? Because we always had machine learning, and what you're presenting, including the heterogeneity, speaks to the epidemiology concept of being intentional with your model and or like doing the verification, and also looking specifically at effect modification, which is what heterogeneity in part is. Any thoughts on that?
Can you be thanks for the kind of introduction to your question, but your precise question would be,
do you think we never should have started using the term AI? Artificial intelligence is like, just throw everything in, because we always had machine learning. What we should have done is said, let's use machine learning in the kind of intelligent way that you are. And it's us providing the intelligence.
Yeah. But wow, it's a nice way of putting it, of saying it. You're right. I should not have used the word AI. Actually, you're right that this is machine learning. Maybe I'm like all the rest.
It's not you. No, it's our world.
Yeah, it's our world. Yeah, so I'm kind of in the world and I use AI all the time. But AI will come one day. I think when we say generative AI, it starts to be a level more than machine learning. And then agentic AI, I don't think we should call it agentic machine learning. It starts to be on the level of artificial intelligence. But I understand that you're right that we have not reached the level of human intelligence. So maybe we should not call it at all AI until we reach that point. But it seems like we're going to get to it. But you're right, definitely machine learning to help clinical research, nothing too fancy in the end. It's to help clinical researchers and computer scientists to do better machine learning. That could be useful for super big AI systems one day. I think there's a role to play with those specialized systems, models that we can build here together to be integrated into bigger agentic systems one day. AI agentic systems one day.
Dr. Smith, did you still have a question?
Well, I did, but I'll catch up with him later. I just wanted to say thanks for a stimulating talk.
Merci.
Nadine, did you? I just have a very general question. I'm trying to understand who is using this app that you're developing. Are you, receiving requests from researchers in the RIMUHC? Are you applying this yourselves, or are researchers who are downloading it from you using it on hospital data? And three parts. I mean, I suppose there are competitors, there are people doing this across the globe. What is unique about this effort?
That's an excellent question. So the first way the first response to your question is, at this time it's really me that uses the platform to facilitate my work with my different collaborators and the clinical collaborators, so that we try to work in a given environment. We're still at the level of development. We say we are at level version 1.5, but we plan to make it write a paper actually about it on version 2, and then perhaps other researchers will use it more. And why not? I want to offer it as a platform to the RIMUHC, maybe other, so that it's available for other researchers. Of course, it's already available online, but let's say we're going to make it a bit more formal soon. But at this time, we're using it for our own purposes because we think it helps us to work. So I think it can help others to work together. And then what distinguishes Medomix from the rest, or its main strength, I think it's this here. So you start in the front-end interface that you've seen in the video. We could look at it again maybe later, but you have a front-end interface where you can design pipelines where it can be a computer scientist, it can be a physician, it can be a team that works together to create those pipelines. I think that's it's not the magic, an interface. Other people do interface, but here the kind of magic is, okay, you create the pipelines together in a user-friendly interface. If you want, you can go down the road here, generate the code that from the pipeline that you've created among the team, and then you directly have the notebooks associated to it, the Python codes associated to it that you can perhaps afterward refine. So it's as if me, as a computer scientist, I would get Python notebooks from my favorite physician because he built the pipeline himself. He pressed the button code generator. Then I can start a problem with some code, refine it, perhaps improve it. And I know that what I've received is directly responds to the problem, basically, because it's the physician or the clinical researchers that has built the pipeline. So it's this link here that I think is interesting for Minox. Yeah, also, yes. There was maybe we'll give him a chance.
Thank you for your presentation. I do have a question about the outcomes of the model which the model can predict. You just gave an example of the mortality, if I remember correctly, and what other outcomes can the model can predict?
So in oncology, the first example I gave actually at the beginning, predicting in patients that have soft tissue sarcomas, they arrive at the hospital. So we image those tumors with MRI, for example. We extract features and we try to predict if they're likely to develop metastases, here specifically lung metastases, because it's a problem with the soft tissue sarcoma. So predict right at the start if they have more chances to develop lung metastases, give this information to the physician, and then the physician can perhaps adapt the treatment in consequence, perhaps do more chemo and so on if there's more chances of developing lung metastases. So that's an example of a predictive model that is built from retrospective data. Obviously, we had a cohort from which we knew with all the images of the patients before the treatment, and we know what happened to those patients, and we build the relation between the imaging features and those that actually develop lung metastases. And then after you have that predictive models that can support the decision of physicians later on. So that's another example. And there's plenty of other examples in cancer where there's these type of predictive models. It can be good response to immunotherapy, good response to chemotherapy, good response to this and this and that. That's predictive modeling.
Regarding the Medomics app that you have, you say that it generates like the Python code. So you give the data in those 3 scales, like for example, multi-omic data, the like imaging data, like higher level data. Mm-hmm. So it pre-process everything, like quality control, pre-process the imaging data, everything. Then
there's a certain.
So what code it generates? Like when it generates, for example, the clinician like wants to see some patterns in the data, okay, has different kinds of data, gives the data and it generates the code. What is that code like it?
So we try to ingest as raw data as possible here.
Okay.
But researchers in some point are responsible at this point. There's an input module right here. To prepare the data. We have tools in the interface that allows you to curate the data and see if things make sense and prepare tables for machine learning. Basically.
Okay, so the researchers and clinicians do the pre-processing kind of step, and then like the final step would be using the Medomics, like,
because who else would do it if not the team? Right?
Yeah.
Prepare the data correctly.
So it's not like the people with zero knowledge can give a data and like get something out of it.
No, because there's always, you need to understand your data. And that's why if we get clinicians to come here in the input module because they understand the best data, they're going to be able to help in preparing it for machine learning, probably in a better way than us computer scientists could do.
Okay.
Okay, great. Thank you.
You're welcome.